Hash tables are a fundamental data structure used to implement dictionaries, which store key value pairs. Their most remarkable feature is the ability to perform insert, search, and delete operations in average constant time, denoted as O of 1. This efficiency is achieved through a hash function, which maps keys to specific indices in an array. By doing so, hash tables enable fast lookups without the need for sequential searching. Hash tables are widely used in applications requiring frequent, rapid data retrieval, such as caching, database indexing, and networking. However, designing an effective hash table requires careful selection of the hash function and strategies to handle collisions, ensuring both efficiency and reliability. Throughout this presentation, we will explore these foundational concepts and their practical applications. Direct addressing is a straightforward technique for implementing dictionaries when the universe of keys is small and well-defined. In this method, an array is used where each index corresponds directly to a possible key. The array T ranges from index 0 to m-1, with m representing the size of the universe U of keys. This design allows operations like search, insert, and delete to execute in constant time, O of 1. While efficient for small key spaces, direct addressing becomes impractical when the universe of keys is large, as the required memory increases significantly. For example, if you includes all possible phone numbers, the memory cost would be prohibitive. This limitation leads to the adoption of hashing, which reduces storage requirements while maintaining efficient operations. Hashing addresses the limitations of direct addressing by using a hash function to map a large universe of keys into a smaller, fixed-size array. For a given key k, the hash function h maps k to a slot in the array, denoted as h of k. This approach reduces storage requirements to theta of the number of keys actually stored, k, and maintains an average search time of O of 1. For instance, a hash table storing student IDs only needs a fraction of the memory required by a direct address table. Hashing is especially useful in systems where storage efficiency and quick lookups are critical, such as inventory management and search engines. Its balance of performance and memory usage makes it an essential tool in data structure design. Collisions are a common challenge in hashing and occur when two distinct keys map to the same slot. Since collisions are unavoidable, effective resolution strategies are necessary. Two popular methods are chaining and open addressing. Chaining resolves collisions by associating each slot with a linked list of elements hashing to that slot. This allows dynamic storage within each slot and simplifies implementation. Open addressing, on the other hand, resolves collisions by probing for an alternative slot to store the element. Both methods have their advantages, and the choice depends on the specific use case, including memory constraints and expected data distribution. Chaining is a simple and effective method for collision resolution. Each slot in the hash table is linked to a list that stores all elements mapping to that slot. Insertion involves prepending the new element to the list, while search traverses the list to find a match. Deletion removes the element from the list. On average, the performance of chaining is O of 1 plus alpha, where alpha is the load factor defined as the number of stored keys divided by the number of slots. Maintaining a low load factor is crucial for performance. For example, a hash table with 100 slots and 50 keys has a load factor of 0.5, which ensures efficient operations. However, as the load factor increases, collisions become more frequent, leading to longer lists and degraded performance. To mitigate this, hash tables often resize dynamically, keeping chaining a reliable strategy for various applications. The success of a hash table depends heavily on the quality of its hash function. A good hash function must achieve several key objectives. First, it should spread keys uniformly across all slots to minimize collisions. Uniform distribution ensures that the load factor remains balanced, which is critical for maintaining O of 1 average operation times. Second, the hash function must be deterministic, meaning that the same key always maps to the same slot. This consistency is essential for accurate data retrieval. Additionally, the hash function must be computationally efficient, as its performance directly impacts the overall efficiency of the hash table. Lastly, the function should minimize collisions to reduce the need for collision resolution strategies. By meeting these criteria, a hash function can ensure that the hash table operates efficiently under a wide range of conditions, making it a versatile tool for data storage and retrieval. The division method is a straightforward and commonly used approach to designing hash functions. The hash value is computed as h of k equals k mod m, where m is the number of slots in the hash table. This method is computationally simple and effective when m is carefully chosen. For best results, m should be a prime number that is not close to a power of 2, as this reduces the likelihood of clustering. For example, if m is a power of 2, the the modulus operation may only use the lower order bits of the key, leading to uneven distribution. Choosing an appropriate M ensures that the hash values are spread uniformly across the table, minimizing collisions. The simplicity and reliability of the division method make it a popular choice for general-purpose hash functions in systems requiring consistent performance. The multiplication method offers an alternative approach to hashing, leveraging fractional numbers for a more uniform distribution of keys. The process involves multiplying the key k by a constant a, where a is a real number between 0 and 1, extracting the fractional part of the product, and then multiplying it by m. The resulting value is floored to determine the hash value, expressed as h of k equals the floor of m times the fractional part of k times a. This method is less sensitive to the choice of m compared to the division method, making it more flexible. A commonly used value for a is the inverse of the golden ratio, approximately 0.618. This choice avoids patterns in hash values and promotes a uniform distribution. The multiplication method is particularly useful in applications where precise control over m is difficult, such as dynamic systems with varying input sizes. The multiply shift method is an efficient implementation of hashing that takes advantage of modern hardware capabilities. It computes the hash value as h sub a of k equals the floor of the product of k times a, modulo 2 raised to the power of w, shifted right by w minus l. Here, w represents the word size, l is the desired size of the hash value, and a is an odd constant. This method is computationally efficient, relying on bitwise operations such as shifts and modular arithmetic. Its simplicity and speed make it ideal for high-performance applications, such as networking and real-time data processing. The multiply shift method is particularly valuable in scenarios where the hash function must operate at hardware-level speeds, ensuring consistent performance across diverse workloads. Random hashing introduces a probabilistic element to hash table design by selecting the hash function randomly from a predefined family of functions. This approach is particularly effective in preventing adversarial scenarios where input keys are crafted to exploit weaknesses in the hash function. By introducing randomness, the hash table achieves consistent average case behavior regardless of the input data. For example, in cryptographic applications or online systems, the nature of the input data can vary significantly. Random hashing ensures robust performance even in such unpredictable environments. While implementing random hashing requires careful selection of the hash function family, its ability to adapt to varied workloads makes it an essential technique in secure and efficient hash table design. Universal hashing provides a robust framework to ensure good average case performance for hash tables. A family of hash functions, denoted as h, is called universal if, for any two distinct keys k1 and k2, the probability of a collision, where h of k1 equals h of k2, is at most 1 over m. Here, m represents the number of slots in the hash table. This property ensures an even distribution of keys across slots, minimizing performance degradation caused by clustering. Universal hashing is especially useful in adversarial situations, where input keys may be designed to maximize collisions. By randomly selecting a hash function from a universal family, we mitigate such risks and maintain consistent average case performance. Applications like network security and distributed systems benefit greatly from this approach, as it ensures that hash tables remain efficient and reliable even under challenging conditions. A practical implementation of universal hashing uses modular arithmetic. Given a prime number p larger than the number of slots m, a hash function h sub a b of k is defined as the floor of a times k plus b, modulo p, then modulo m. Here, a is a non-zero integer modulo p, and b is an integer modulo p. The family of such functions, h sub pm, is a universal family. This approach guarantees uniform distribution of keys and is computationally efficient. For instance, database indexing systems often rely on this method to handle large datasets with diverse key distributions. By choosing suitable values for p, a, and b, the hash table achieves minimal collisions and predictable performance, making it a reliable choice for many applications. The 2 over m universal family is an extension of universal hashing, based on the multiply shift method. Hash functions in this family are expressed as h sub a of k equals the floor of the product of a times k, modulo 2 raised to the power of w, shifted right by w minus l. Here, w is the word size, l is the desired hash value size, and a is an odd constant. This method ensures that the probability of collision between two distinct keys is at most 2 over m. The efficiency of this family, combined with its strong theoretical guarantees, makes it ideal for high-performance applications such as data streaming and distributed systems. The reliance on bitwise operations ensures rapid computation, while the probabilistic nature of the design provides robust average case performance across varied datasets. Hashing long inputs poses unique challenges, as their size may exceed the limits of single-word or prime modulus hash functions. To address this, number-theoretic approaches extend the principles of universal hashing, breaking the input into smaller chunks. Each chunk is hashed separately, and the results are combined to produce a final hash value. This method ensures efficiency and uniformity, even for lengthy inputs. Another solution is cryptographic hashing, which employs robust pseudorandom functions to generate fixed-length outputs for arbitrary length inputs. Cryptographic hashes, such as SHA-256, are collision-resistant and widely used in applications requiring high security. For instance, they ensure data integrity in systems managing large text files or digital records, maintaining both performance and security standards. Cryptographic hash functions are specialized algorithms that transform inputs of arbitrary length into fixed-length outputs. These functions are designed to be highly secure, with properties such as collision resistance and pseudorandomness. Examples include SHA-256, which generates a 256-bit hash, and ICE-based functions, which leverage hardware for speed. These functions are essential in systems where data security is paramount. For instance, in password management, cryptographic hashes ensure secure storage by transforming plaintext passwords into irreversible hashes. Similarly, in blockchain systems, they enable the creation of tamper-proof transaction records. Their robustness, efficiency, and wide implementation make cryptographic hash functions a cornerstone of modern secure systems. In conclusion, hash tables are powerful data structures that provide efficient solutions for storing and retrieving key value pairs. Their performance relies on the combination of a well-designed hash function and an effective collision resolution strategy. Techniques like chaining, open addressing, and universal hashing allow hash tables to maintain O(1) average operation times under diverse conditions. The versatility of hash tables extends to various domains, including database management, caching, and network routing. By understanding the underlying principles of hash function design and collision resolution, developers can create robust systems that meet the demands of modern computing. Hash tables are not merely theoretical constructs but practical tools that continue to play a critical role in data management and application performance.